Hello everyone. My project is reinforcement learning based edge cloud task scheduling. In this project, I built a three-node cloud lab environment with an IoT node, an edge node, and a server node. The goal is to decide where each incoming task should be processed. Locally on the IoT node, on the edge node, on the server node, or rejected. I modeled this problem as a macro decision process and used value iteration to compute the scheduling policy. Then I compared the RL policy with several baseline methods, including always no-code, always edge, always cloud, and random scheduling. Here's the experiment design. There are three nodes: IoT node, edge node, and server node. Tasks arrive at the IoT node at each decision epoch. The RL agent chooses local edge server or reject. I deploy the RL agent at IoT node, connect the data of the edge and server, and also send the data back to the IoT node for RL agent computing. The top node of the three nodes are IoT, edge, server. The goal is to compare the RL perfects with the four baseline methods, which are always local, always edge, always cloud, and random baselines. Cloud type and the node rows. The IoT node used for the IoT compute and its scheduler. It generates tasks, local execution, and the MDP, the value iteration, and the baseline compute. The edge node executes the edge offload tasks. The server node used to execute the cloud server offload tasks. The three nodes all use D710 hardware. The network setup and the measurements. There are the three nodes IP. We use the command to routine set up the routine and get the network delay. The total edge compute time is equal to the edge processing time plus the delay time. The server total time is equal to the server processing time plus the server delay time. In the project, I tested the edge delay is 0.237 milliseconds, and the server delay time is equal to the 0.417 milliseconds. For the workload design, there are three different type problems. It's the small represent as small, medium, and heavy. The deadline for the small is 20 milliseconds, and the revenue is 5. The deadline for the medium is 80 milliseconds. The revenue is 15. The deadline for the heavy task is the 300 milliseconds. The revenue is 30. The tasks are implemented as SHA 256 digits computation, such as the small task we can compute the string with 1000 times nonce and get the digits. The heavy tasks perform the heavy computation and have the highest revenue, and the small tasks has the smallest computation. We run the task runner separately on each node and get the CSV format data. that contains the task type action, QDIPs, RTT completion time, DAN9 next QDIPs, and the next RTT. The DAN9s were used to create scheduling pressures. For the MDP state space, it contains the node level, task types, and network level. For the load level, when the Q dips is less or equal than 2, the load levels are idle. And when the Q dips between 2 and 5, the load level is moderate. When it's more than 5, the load levels represent as overload. For the RTT of the network level, when the RTT less than 30 milliseconds, the level is represented as good. And when the RTT is between 30 milliseconds and 100 milliseconds, the network level is represented as normal. And when the RTT is more than 100 milliseconds, the network level is poor. And task type we mentioned before is small, medium, and heavy. So there are 3 node levels, 3 task types, and 3 network levels. So there are 27 total states. The action space and the transition probabilities. The local load action is run the problem on IoT. And the edge action is offload the problem to the edge and compute. The cloud action is offload the problem from the edge node to the cloud node and then compute. The reject is do not execute the task. Here's the function for the transition probabilities. Each measurement row records current state, action, and next state. The next state is derived from the next QDIPs and next RTT. The transition probability are estimated from the real Cloud Lab data. The program calculates the probability of all measurement rows with the same current, state, and action edge. Here's the function for the reward. For the local compute, the cost is 0.1, and the edge action, the cost is 0.3. The cloud cost is 0.6. The reject costs nothing. And there are 3 different situations. It's the reject, complete the task before the deadline, and complete the task after the deadline. When the task reject, there's a penalty. The reward is minus 0.1 times the revenue. When the task is completed before the deadline, the reward is equal to the revenue minus the action cost minus the netting penalty. When the task is complete after the deadline, the reward is equal to the minus 0.5 times the revenue minus the action cost minus the netting penalty. So for the netting penalty, we see the rate is 0.4. So the netting penalty function is equal to 0.4 times the revenue times the completion time over the deadline. The latency term penalizes tasks that use more of the deadline window. The reject receives a small loss opportunity penalty, but it also avoids compute cost and deadline miss penalty. Here's the value iteration of the RL agent. This function is for the Bellman update, and this function is for the optimal policy. The Bellman update computes how good each state is, and the optimal policy chooses the best action for each state based on these compute values. the discount factor gamma is equal to 0.9. The output of the optimal policy are saved as JSON file, and policy maps each state to one action. Here's the optimal policy results, and here's the measurement is the RL-AG measurement results. So the baseline comparison result is shows the RL agent larger than the profit larger than the average local and random compute. But there are also has a strong baseline, which are always cloud and edge. That's all very strong on Cloud Live. The always local data hit rate is smallest because some medium or heavy tasks cannot finish on the IoT node within 10 nights. Therefore, RL policy can offload these tasks to the edge or cloud server nodes. Conclusion. According to the results, the RL gets profits much higher than Always IoT and random computing. Always Edge and Always Cloud achieves the higher profits because the Cloud Lab Edge or the server nodes were powerful and had very small RTT. But that does not mean the RL is not correct. It shows the policy performance depends on the measured system conditions. The three nodes are run in the CloudNet machine that are more powerful than the real-world IoT. So, the project demonstrates the RL scheduling can improve the profits, but it also depends on the system environment and the MDP design.